Okay, so it's 4 o'clock. I'll just wait for 1 or 2 minutes just for people to settle in. Yeah. Satya is here. Huh. It just makes it so good. The 5 minutes delay. Yeah. Okay, I think I will start. Okay, so good afternoon, everyone, and I welcome all of you for another edition of the NSF Wednesday Colloquium. And just to say that this is not just another edition, it's actually a very special one. We have Professor S. Ramakrishnan, who is the current director of TIFR, is going to give the colloquium and especially reminisce some of the work that he was involved in this institute. I think this would be a fantastic ground for all of us to sort of learn about him, both professionally and some bits of personal history. So I really would like to welcome everyone in the Zoom and into this auditorium for this special colloquium. Now, the NSF Wednesday Colloquium, we all know, is an age-old tradition in the Institute. It was started by Professor Homi Bhabha, our founding director. And just like today, when all the different faculty members and students from different walks of life in this institute have joined in, that was the original idea, that all the natural sciences faculty members, students, and researchers will get together and listen to very highly engaging talk in one of the subdisciplines of physics, chemistry, or biology. And so today is a special one, but I have a special person to introduce, Professor Ramakrishnan. We have a younger colleague of Professor Ramakrishnan, Ramki, as we lovingly call him, to introduce him. And colloquium introductions for members within institute is not a fashionable thing to do, but this one is a special one. So I would like Pratap Rai Chaudhary from the Department of Condensed Matter Physics and Material Sciences to give the introduction to Ramki.
Hi, so good evening, everyone. I don't think Ramki needs any introduction in this audience, but for those who might be new here, let me still say a few words. So Ramki is one of the pioneers of low temperature physics in India. And it's sort of overstatement to say that within India, low temperature physics is essentially synonymous with Ramki. So he started his career, his research career in TIFR. So what's interesting is for someone who is always identified as an experimental low temperature physicist, most people possibly don't know that he started his career by writing a paper on theory of superfluid helium. And in those years, it was a paper which dealt with the experimental verification of a prediction that very dilute helium-3 solution in helium-4 could undergo a superfluid transition at microkelvins. So this was many, many years before India had any place which had temperatures of the order of microkelvin. But very soon, Ramki realized that thinking about low temperature physics is not his calling. He has to actually do the real stuff. So he soon moved to experiments, and he did his PhD here in 1985. Since then, he has worked on numerous areas spanning charge density waves, superconductivity, and in particular on intermetallic compounds, compounds that are essentially alloys, either ordered or disordered alloys of metals. So his early work was on coexistence of magnetism and superconductivity in rare earth iridium silicon compounds. Later on, he started working on charge density wave in similar materials. And what is almost unimaginable nowadays for many of us is the amount of resources with which Ramki had done all this phenomenal work for at least his the first 2 decades of his active research career. For those who had gotten enormous support from the Institute from the day we joined, this is almost unthinkable. Nevertheless, so in the 90s, when the institute situation in terms of helium was very tight, Ramki was started doing extensive international collaborations, which brought TIFR and Ramki a great deal of visibility in the international arena. But in some way, TIFR also lost because it was almost a forced collaboration that Ramki had to do to keep his program surviving. At that time, because of various reasons, the helium situation was bad, there was no crystals, and many work which actually were conceived and moved by Ramki had TIFR got only part credit for that. At any rate, later from 2000 onwards, Ramki took up the project of a very ambitious project of ultra low temperature physics, which is to reach temperatures which are less than a millikelvin in the order of microkelvins, hundreds of microkelvins. And this is a project that actually reaped very rich benefits. So interestingly, when Ramki was a postdoc, he had suggested to his postdoc supervisor, who was an extremely gifted low temperature physicist, to look for superconductivity in bismuth. This was several decades back. And of course, at that time, they had other priorities and it did not happen. So Ramke, when he got his own, he performed this measurement, I think, 4 decades after he first proposed it. And it, it demonstrated for the first time that you have superconductivity in bismuth, but at a very, very low temperature. It's a very unusual superconductor. And this was a very high profile and very highly cited paper published very recently in Science. So something that got here for a lot of visibility. So I'll stop here and we'll hear the rest from Ramki. So over to you.
Thank you. Thank you, Pratap.
Yeah, thank you, Pratap, for a very nice introduction. I think you summed up the way I felt, in my whole career here in TIFR. So when you can hear, right? So when I joined here, as I said initially, I was interested in fourth sounds in helium-3, helium-4, because there was a prediction that helium-3 also will become a superfluid in that mixture. So far, it has not happened actually. But then we said, okay, let's try to look at the superfluid hydrodynamics and predict that sound wave. So that part we did. Then I decided to work on superconductivity as an experimental project here. So that time, the low temperature physics group is a part of the nuclear spectroscopy group headed by Professor Girish Chandra, who himself was an excellent low temperature physicist, and he did his postdoc in Kapitsa Institute for nearly 3 years in Moscow. And he had the distinction of speaking Russian. He speaks fluent Russian. So any Russian delegates from TIFR, he has to be there, and he is the man who do that. And Girish Chandra, as an advisor who is always interested in building things. So, when I went to the lab, there was nothing which is there to look at superconductivity and so on in this. So he said, you build it. There was a very old valve AC susceptibility bridge and valve circuits, and it is really in a precarious state, so it could go any moment. So quickly, then we decided to make a electronic version of it, and I was fortunate that there is a guy called Channabarthi who was a scientific officer at that time, who was equal to any task I set it up. So then we quickly made an electronic version of the bridge. Then we were trying to borrow some resistance bridge from Professor Ray, who was a senior at that time. And then Ray wanted this bridge back. And then Richchandra coolly said in one evening, build an AC bridge. No. So because those days foreign exchange is going to be extremely scarce. So then we went, myself and Chanavati, to our library, look at Review of Scientific Instrument. There is a standard journal. So try to pick up a circuit from there and then modify in your own way. Then run into Lamington Road, where you can get these ICs and so on, and all the good ICs they have, but the prices, there is nothing fixed, you see. So it depends on how eager we are. So we have to pretend that, it's okay, chalega, OP07. If it is not there, we'll go and so on. So show a little bit of disinterest, then finally buy it at some price and then come back and put it up and make that AC bridge works. It has the same probably precision as the fancy ones you can buy from outside. So everything, let me just go back to this. Everything was built, right from, as Pratap said, let's come back to this later. Let me just tell you that, I belong to one of those rare species now who has spent more than 4 decades in this institute at various capacities. I'm not going to talk about administration today. That I'll reserve it for some other rainy day. That's also equally interesting, but not as interesting as this one. So what happens when you spend 4 decades? So you join as a brash, research scholar who is very impatient and want to do something next day and so on. So, and also you find that rules are becoming really hampered, and generally you have a dim view of the administration. Okay, so this dim view, I will come to it later. Then, so then you progress. Where am I? Sorry. I think I made a mistake. Okay. Okay. So then you became an associate professor. Then you are really mellowed. Then you look at all aspects and so on, and then listen to both sides. Students on one side, your bosses on the other side, and you can see that look itself. It's generally becoming a really mellowed. And so then, of course, you become at least an interim director, and of course then you have to look stern. Apparently, it is one of those rare photographs. My wife says that if you are like this, I wouldn't have married you. So so the point is that you have to look stern. So I managed to look a little bit stern, and so let me just go to this. So I did the first experimental thesis on superconductivity. These are compounds which are cubic in nature. And those days, they were the high species superconductors, at least some of them, like niobium-3, germanium, and so on. So we were interested how the normal state properties of these materials are related to their superconductivity. So you need to have a resistivity setup, you need to measure the susceptibility and the heat capacity and so on and so forth. So what we did was, again, I got into some problem. Sorry, okay. So you start developing many facilities, right from AC susceptibility, resistivity. Then, I'm extremely glad that in 1984, we could automate this. This was the biggest thing which which found favor with my students later, because those days we used to write in ledgers. You will see that about 20 notebooks or 30 notebooks were there still with my written record of resistivity, temperature, or whatever it is. So when this Cistron donor, which was a very old IEEE controller, which came in the market. So quickly, myself, Channabati, tried to do this. The only hitch we had is that when we generated the data, those days there was a computer called Cyber. And we wanted to send it to that so that we can take it from there and plot. They didn't allow. So they said, oh, we might corrupt the system and so on. But it took some convincing. After 6 months, we could do that fully automation. Then, of course, everything we need to build, UHV, annealing furnace, we can't buy it. So we need to use the turbo pump. And so then I was telling Girish Chandra that we need a cryo pump. So he said, brought a bag of zeolite, built a cryo pump. So we did all that. So it was fun while it lasted. So because of this, we had really state-of-the-art AC susceptometers and so on. We had a very fine temperature control of like 1 milli-K at 4K. Then it opened up a new, new kind of approach. And luckily, Arun finished his postdoc in Imperial. He came back. So we were very interested in vertex physics, basically how the vertices form a lattice and what is the structural transformation, all bulk measurements, which of course, Pratap has done a beautiful STM experiment to show really what is happening. We were just looking at the bulk and then trying to study. Those days, even that was not done. So since I had things which are ready-made for this, we could have a huge success there. That is the vertex physics. With we had shared many students with Arun. And, then, as Pratap mentioned, that I was interested in multiple phase transitions, how, let's say, a charge density wave coexists with the superconductivity or magnetism. All this I have given several colloquiums, maybe about 5, 6 in my lifetime. And that resulted in a review sometime back. There were about 4 or 5 students involved in this. And he wrote maybe about 2 dozen physical review papers on this. I don't remember now. And then I moved on to strongly correlated superconductors. So I just wanted to know how one can realize heavy fermion superconductivity in a D-band system. I was not successful, but we came with this interesting system. These are compounds where the distance between the primary element, like rhodium, the distance is even shorter than what is existing in rhodium metal itself. So that is the reason why we wanted to see what happens to the bandwidth and so on, how it behaves. It turns out that really it's an unusual system. It's still, we don't have a proper theory for it. Of course, if you ask Bhaskaran, he will say that these are all bad actors. They don't follow the script. So actually, I'm guilty of producing many bad actors in this whole thing.
Can I ask a question? Can I ask a quick
please.
question? This rhodium compound with sulfur, is it like the sulfur, there is one sulfur attached to the rhodium in every lattice point? How is this arranged?
It's a cubic system with the 64 atoms in the unit cell. Actually, this is a catalyst. They use it to in chemistry, it is done very well because they have done the structure analysis and everything. It shows that, it's used in the production of methanol.
Methanol, okay.
And because this catalyst doesn't get, consumed so much, and then regeneration is easy, and that's how it is. And that catalyst earlier, about 1950, Matthias found superconductivity.
Okay.
But then there was no understanding of what is superconductivity there and so on.
Okay.
Actually, in my 5th colloquium, I did talk about this. So and then let me come to this final thing about bismuth. So bismuth has a curious history because when I was doing postdoc with Nobel, which I think Pratap mentioned, so I did suggest this bismuth problem because this was a vacant in the periodic table, and I thought it's an interesting system to work on. So Pavel looked at me, and he had a similar fridge, which I have I've set it up here, 50 microkelvin. He's a pioneer in ultra-low temperature physics. So he said, oh no, the Helsinki group has not found till 10 milli-K. I don't want to invest that much time. So let's look at problems which we can immediately work on. So we were interested that time in nuclear magnetism. So we stopped that. Then when I got this superconductivity, he's the first guy who congratulated me from there, wrote a long email that, it's great that you could do this and so on. And, just praised me. So it was, I considered as a very high praise from a guy who is a pioneer in this field. Okay, so now 2017, we got this science paper. And of course, when we first we sent to Nature, all of us we do, and the Nature refused to review it. So we were really upset. My student whom was upset. Then we sent to Science. It went smoothly. And of course, they wanted nearly 4 months. We have to do everything, including info. The editor simply said, this goes into a periodic table, you better be sure. So then we said, you do elemental analysis. We showed there is no impurities and 6-9. So about 4 months struggle. The bonus is that they said you don't have to pay charges. It's free. It's on us. We will do it. So I think that was the thing there. Now the Nature Physics editor came here and so on. He did apologize that the way it was handled. Then the current Nature editors wanted this anisotropy. So let me come back to this later. So we go back to Camerling owners, because any superconductivity talk cannot be without his photo and this. Everybody shows this very nice resistivity data, but nobody realizes how the measurements are made. He is talking about 125 milliohms there, which is going down to 0. So this resistance of mercury, right now, the best ones are residual resistivity ratio of 1000. And for him, at least that time, it must be at least 100, which means it is 125, 12.5 ohms at room temperature. Try to achieve 12.5 ohms of mercury resistance. To get 1 ohm of mercury resistance, you need 1 meter of mercury in a 1 millimeter square cross section. So imagine how much struggle he has gone through to have 12.5 ohms, and it goes to 125 milliohms, then he sees low. It's a marvel. Actually, and I went and saw, because I was a Camerling owners professor for 5 years. I went and saw his lab. It's preserved as a museum there. It's amazing things he has done. I mean, to get this transition, you won't believe they have copper bellows at that time. I mean, which is unheard of. I never thought that such things existed. And he is. That's why he is Camerling owners, I suppose. Yeah. Okay, so I will stop. So then once the mercury started, this graph we might have seen from many people, including theoreticians, show these things, though theoreticians didn't contribute much to this. But the point here is that you would see that superconductivity is everywhere. The green ones are the ones which is at ambient pressure. The ones which is shaded are the ones either in thin films or in high pressure and so on. If you look at this, even things like iron, chromium, they are all superconductors, which are supposed to be magnetic and so on. So the biggest hole is in bismuth, because bismuth is superconducting only under pressure before. It can go up to very high temperature of those days, about 7.2 K and so on. I'll come back to this slide a little later. So I think superconductivity picked off. Now you see in the, all in YouTubes and so on. So earlier Camerling owners did, go to lower and lower temperature, look at this phenomena. Now these guys are trying to do is to squeeze more and more and push the temperature up. So I think both are in the different critical region. One is at low temperature, one is at high temperature. And people have gone up to nearly room temperature, 15 degrees centigrade. And there is some news that something is now superconducting at 300 K. This 15 degrees is still under some cloud. So, but I think this would be, it's not surprising that with the amount of hydrogen they have, they would reach even higher temperatures. But the important point here is that we would love to see a superconductor at ambient. So let me just trace this history back. So till 1985, the superconductivity was really a low temperature phenomena. You need liquid helium, otherwise you can't do that. So came the high TC, which was really a surprise. And then, it just pushed up to this. Then this high pressure has taken over. And well, we were the guilty ones to brought this superconductivity down close to 0 with bismuth. And the other one, which is equally interesting, is what they call Q carbon. It's an amorphous form of carbon which will melt, suddenly cool, it goes to a special allotropy version of carbon. The important point is that this carbon absorbs a lot of boron, and that gives rise to this fairly high TC superconductivity. 55K is no joke. So let me just go back to the theory a little bit. That is the only equation I will show this time. So this is a celebrated paper. BCS theory is a poetry in art. It's very complicated phenomena like superconductivity, and these three theorists really did a marvelous job. I mean, it's not that it cannot predict the transition temperature. Who cares? But it gave the idea of how this pair formation can happen. It had its own predictions like energy gap and so on and so forth. So it captured what was eluding for nearly 45 years. 1911 it happened, and this theory came in 56. It deserves in fact, it should deserve 3 Nobel Prizes. If you ask me, for the 3 guys should be given separate. The paper is really fabulous. They picked this idea from Froelich, who said that, if a superconductor has to happen, the electrons have to attract, they have to have a bound pair. Yeah, please.
Yeah, sorry. It's a very naive question. So this the 3 gentlemen they gave the theory, but we know the Cooper pair, right? So I was just looking at the Higgs boson, because there's several theorists are responsible, but Higgs is the first person to really say the particle. So I was wondering whether Cooper is responsible something special. We call it Cooper pairing.
Yes.
So if you could.
So I didn't say the previous paper. Cooper thought that how 2 electrons can form a pair. Cooper showed the way that it can form a pair, but Cooper didn't take the, there is 10 to the power of 22 electrons in the system. There's a large fraction undergoing Cooper pair and so on. So the general theory was provided by these 3 people. Cooper showed that how it can happen. So that's why it's called Cooper pair, is a special name for him, because he's the one who published that paper. So Bardeen picked up those ideas and also the Froelich ideas, that how electron, couples to another electron using a virtual phonon. This is an extremely, quantum mechanical concept. But one way to see this is to look at, in a simple way, that you consider metal as arrangement of positive ions and the electrons are just moving around. So this electron goes through this place. Suddenly there is a positive charge gets attracted. The next electron comes here at a later time, sees that, and then that's how these 2 electrons are coupled. So in theory, they call it retardation effect. It's a retardation thing, So one can visualize this coupling in a semi-empirical way. It's a physical picture just to understand, but the real thing is it's a quantum mechanical phenomenon. So BCS theory was saying that this is the way the electrons can get attracted to each other. The important assumption there, which is later known as the adiabatic theorem, is that the phonon velocities are much, much smaller as compared to the electron velocities. So once the electron passes through, the phonon cannot relax back to its original position before the other electron comes. That's how it sees the positive cloud. Imagine if phonon velocities are comparable to electron velocities, then the theory is out of the window, right? Because the electrons, the ions will relax, you won't have an attraction. That is where the bismuth is coming. If you look at the periodic table which I showed you, in all metals, the Fermi energy is much, much larger than the lattice energy. Not so for bismuth. You will see that later. That's why we are interested in the superconductivity of bismuth. We know that if we can show it is superconductivity, it cannot be a standard BCS model.
Okay, Ramki, before you move on, just for people who are outside the community, could you just enumerate the concept of the temperature dependence? Where does the temperature dependence come from with respect to the electrons are seeing each other, are
Right.
bound state? So what happens at low temperature? What happens at high temperature?
Yeah, so the high temperature, the electrons, above the transition temperature, the electrons, we are talking about conduction electrons. So the conduction electrons are free to move. Then you have a simple Drude small model where the resistivity increases with temperature because there is a scattering. So what is happening when you go below this temperature? Then you have this, the Fermi velocities and the ionic velocities are in such a way that there is a possibility that this kind of interaction can take place. So that is the reason why below a particular temperature, this attraction sets in and then do that. The binding energy you can define in form of KDTC. So the binding energy of this so-called this Cooper pair is related to temperature. So when you go below that temperature, then it kicks in. But this will work only for the. So this is what, as I said, Cooper showed that, when you have an attractive interaction, this Fermi C is, unstable. It is better to form this pair rather than exist as individual electrons. Then the BCA showed that with all the electrons put together, how that it can happen. They took a very simple toy model. The potential is within the shell, it is negative and then zero elsewhere. And they predicted this delta, which was verified by the tunneling experiment. Actually, Pratap and also Karthik Raman now with an STM, they can, they see it every day and night. And then they gave a small expression for this TC. So, but then people misunderstood the theory. They thought this TC is a God-given number. Every experiment should match. I mean, most importantly, a well-known experimentalist called Bernard Mathias, who is the father of all the superconductivity discovery. He must have discovered thousands of superconductors. He himself took that as a gospel, and he used to criticize. I was told that in one of the meetings there will be some small session where the theorist will say about computing a TC of one particular combination, but Matthias will get up and say, suppose I make C and D, what will be the TC? And most of the time, the theorist will not know where the C and D in the periodic table itself, he is finished. So, but then, he has in some sense misunderstood what the theory is all about. Theory is telling you that there is how the things can fairly form. The TC you can't do because they have made a very simple assumption, just to show that how the theory can lead to this. Finer things, I think we need to look at each of these elements or each of this compound has its own peculiarities. I think, this has become now well known because people have tried chemometrics. Now they are doing machine learning to find out TC of superconductors. So far, I don't see a single success. Okay, you have put all the properties of superconductors and make a cooking of this, and still you don't get it. So how do you expect a theory which was trying to attempt how the things are formed to give you the correct TC? That can never happen. So then you see, if you look at TC for aluminium, the calculated TC is 7.5, whereas the observed one is 1.2. So the theory is, you should be glad that they are in the same order of magnitude. That is the way you should think. So then came Macmillan, who said that, we need to apply certain corrections to it, try to look at realistic phonon models and so on. He gave this expression where theta D is the temperature, Debye temperature. Lambda is what is known as an electron-proton coupling constant. Mu star is the screen Coulomb interaction. When you have 10 to the power of 21 electrons, the Coulomb interaction is screened. Electrons of one of them is screened by the other. So you have an effective Coulomb parameter, which is mu star. So if you put that, let's say aluminium, we get 2.9 K. I would say pretty good, right? And things like lithium, there I think there is a problem. Lead is very good. So is magnesium, there is a problem. Bismuth is even more a problem because theory predicts that, it can never become a superconductor, whereas we see superconductivity at 0.5 millikelvin. So, and we move on. The delta was a prediction of BCS. And you see even the elements, they don't fall into the BCS shape. It's not surprising. Basically because they have very complicated structures, Fermi surfaces. You cannot use simple BCS to expect that everything should fall on the line. So this is a interesting thing, like things like iridium, it's an extremely strong coupling superconductor. So let me come to this lithium problem. So the lithium in the periodic table is supposed to superconduct at, even if you look Maxwellian theory is 0.6 K. So the Helsinki group showed that it is superconducting at 400 microkelvin. So the only way one can think of that is that what they find is that, there is a positive Seebeck coefficient. Seebeck coefficient has to be negative for metals. But lithium is the exception to this. It has positive, and then people found that there's a strong electron-electron correlations in this. So the mu star is no longer 0.12, mu star is 0.2. So then you see that the TC is not bad. It's close to what we see in the experimental case.
Sorry, what is mu star?
Mu star is the stream Coulomb interaction parameter. Sorry. Okay.
Here, nearly free electron system, it has only one S.
Yes.
Why is electron-electron interaction large?
So what they say is that the energy spectrum changes when you cool below 1K or some such thing. So the Hall coefficients also changes at that point. So there is some Fermi surface change out there. That's why it's no longer the lithium which you see in the atmospheric, in the ambient conditions. So this took a while. It's only the last PRL came just few years before. I don't remember, 2007, 2008. So they can now say that lithium is special because of this. That is the reason its Seebeck coefficient is also positive. Okay. Huh? No, so solid. Okay, so let me come to this magnesium problem. So magnesium was a hole in the periodic table again. And so what do we do? How do we predict something is going to superconduct or not? So we take a known superconductor, make an alloy. If you form a solid solution, you are lucky. If there's going to be crystal structures well defined, you are not lucky. You are stuck. But magnesium, people tried this. And they said that, experimentally, they said that it has to be below 10 milli-K. So then what happened is that you apply the Maxwellian theory. If you see that if the lambda is 0.3, the electron proton coupling constant is 0.3, it is 160 millikelvin. If it is if it is 0.2, it is 180 microkelvin. But more importantly, if the mu star varies from 0.1 to 0.11, okay, it's so critical that you go from 180 microkelvin to 22 microkelvin. So we made a very pure crystal with Tamil Whale. We tried to surge down to 100 microkelvin. So that was again a failure story. We could never get magnesium superconducting. So at least up to 100 microkelvin, it is just not superconducting. We tried gold also down to 50 microkelvin. It never superconducted. There were many failures. Bismuth is one of the successes. Yeah.
Is that prediction ever be reliable?
It is not. It is not never be. So what we wanted to know was to set a lower limit for the magnesium. So I'm just telling this because, all these predictions, exactly the way you are saying, even if we change mu star by this, if it changes that, so I don't believe that theory so much, so, but then we need to prove experimentally that at least up to 100 microkelvin, we are sure that it is not superconducting. So that was TIFR results. So where are we going in superconductivity? So as I told you, in BCS, we can explain many of it, or extension of BCS, like strong coupling theory of Eliasberg can explain many of the superconducting transition. But there are some holes, lithium, we need to invoke certain electron-electron coloration. Magnesium, we still don't know why it is not superconducting. It should be superconducting because magnesium has a lot of purity. I have to look at the time now. So now it comes to this high pressure. They are squeezing everything and anything under the sun now. So the point is that you don't blame them, because it's like the game which we played with temperature earlier, right? So we try to cool 4K, then we try to find superconductors at higher and higher temperatures. Then odd guys like me wanted to go at microkelvin to find a different superconductivity and so on. So that's why I think people are using hydrides and squeezing everything, every hydride they can get hold of. So some of them are successful on it. Yeah. So see, the point is that the idea of this hydride came from a theory paper. See, because Ashcroft predicted long back that you take hydrogen, squeeze the hydrogen, it will become metallic. And at some point, the hydrogen is supposed to become a superconductor. And it has a high transition temperature because the debris temperatures are huge, 3000 on odd. So these hydrides also have a very high debris temperature when they form. And that is the reason why when you replace this hydrogen by deuterium, you see that the TC is shifting towards the lower temperature, showing clearly that it is the kind of an electron phonon mechanism, maybe a complicated one at high pressures, are the ones which is responsible for superconductivity. So that's why people initially squeeze hydrogen. Many people tried this. In fact, there was a paper which is withdrawn by the Cornell group. They thought they saw metallic hydrogen and so on, but turned out to be it is not. And so this game is still on. The hydrogen thing is even supposed to cross room temperature barrier and so on. So there's long, all over the world, people are doing this. After, this guy showed, there was a Russian scientist in Germany who showed this 205 Kelvin.
205 Kelvin.
Yeah. So it's not clear as to what the structure is all about. That part is still not very clear. Some people say 3S, some people say different this. So, and it's a mixture of two structures. What the recent guy did was he put the carbon into it. So that's how he got this 288 Kelvin. So this research will go on. I think it will go on for some time. So what I'm interesting is that this dedoped Q carbon, that is this is an amorphous carbon. When you melt it, it forms into an allotropy of carbon where it can absorb more and more boron. It's up to 45% boron it can take. And that's how it pushes the superconductivity. So let me just see whether I don't have much time, but anyway, I will talk about bismuth. And then let me tell you about this GLF theory. This is the Kirby
just before
theory.
Going into that,
Yeah.
Is there something well defined in the optical spectra of very high pressured things where you can look at maybe the Raman spectra to look at the electron phonon?
They have done
coupling
that.
part?
They have done that. Actually, in one of the high pressure studies on the H2S variety, they have done that, showed actually Raman is the best way for them to look at the structure even compared to X-rays. So that is the reason why they have done. There are a lot of studies exist on the structure, but it doesn't form a homogeneous compound. Many of them are not forming a single, let's say the single compound is the one superconducting, is not being realized from these studies. But work is going on this. The idea now there is to reduce the pressure and see whether it can raise superconductivity. So some groups are working on that as well. So let me just move on to bismuth. Yeah.
So is it not possible that the high pressure is not really impacting the electron phonon coupling, but it's just making a completely new material? Say sulfur hydride reacts with the carbon, make a new material. That's
extremely, yeah. It's possible. Because see, the point is that nobody knows what the electron phonon coupling constant in this. I mean, they gave a ballpark figure of 2 or something like that, but it's still, we don't know. As you said, it could be the new structure which is giving rise to this. And but they have seen both the Meissner effect and the resistivity. So the data is reliable. Okay, so let me have to come to the bismuth. Yeah.
This is not boron-doped diamond.
See, the diamond doesn't accept more than 5% of boron. So this is a separate allotropic form of carbon. What they do is that they take these nano diamonds and so on, melt it up, heat it up, and then quench it suddenly. Then they have what is known as this Q carbon. Basically, it has large sp3 hybridization and less sp2 hybridization. So then once it has a large sp3 condition, according to the chemistry, which I don't know, the borons are going into that very easily and they can push it up. See, they went up to some 10K or something, you remember, with boron dope diamond. And with this, they can go up to some 30–40%. And that's how they got this 55K. And this is also electron phonon, because the debate temperatures of this are about 2000–3000. It's essentially diamond, carbon. Okay, so which has a large this one there.
You can also dope C60 with something and then basically becomes superconducting.
C60, yes. So C60 is something similar to A15 compounds,
Okay.
which I mentioned there. Okay, so you can go up to something like 20–25K and so on, but then that's all it is. I mean, so we can't go
Beyond that.
push it up.
Very
Yeah, tiny thing.
About the hydration thing.
Yeah.
There's some controversy from Harsh's group saying that the data may or may not be reliable for the last
Yeah,
one.
so 288K, there is a problem. There is a problem. If you look at all the Nature papers, they see that it is under investigation for the past 2 years.
But it has not been settled
It's
one
not,
way or another.
see, the other groups have not, claimed yet. So there's still a problem there. But I think I think they will find something about room temperature, because there are so many hydrides. Now they are gone to ionic hydrides. Okay, so that is another possibility which is cropping up. So I'm sure that it's like the ITC game. You just push it, squeeze anything with you in your hand, and then probably get it. So it's an interesting part, but for me, it is not very attractive because, it doesn't give you a new mechanism or new things which is holding to this. But it is good because it puts the ITC and people are wondering superconductivity. So it's a sellable idea. Okay. So let me just talk about this Gurevich. I don't know whether I'll come to that Gurevich-Larkin theory. It's an interesting part. Then, of course, we have heard from Mohit actually sometime back. I think he had, theorists have gone far ahead in this business. I think they have become more exact and tell you what the limit of all superconductors one can achieve and so on, which is a really a very good thing, because then you know where you are going in some sense. But unfortunately, all these maximum we can never hope to see this in these things. So it is really, it's up there. So we need to see how we can go there. It's a hard task, I would say. So okay, let me come back to this periodic table again. So I told you this bismuth is something different from these metals. Bismuth has 5 orders of magnitude carrier concentration less. So no sane person will tell you that bismuth should be a superconductor, because there's a prevalent notion that you must have high carrier density to get superconductivity and so on. So then reluctantly people then tried, because bismuth is a very nice thing, you can grow very, very nicely. Then the Helsinki group went up to 10 millikelvin and they stopped it. So they said, okay, it's not going to superconduct. So they left it. And this is the sequence how the elements started showing and so on. So the latest one is, not so latest. The rhodium superconductivity was about 350 microkelvin. That was from my mentor, Frank Nobel. Then his competitor in Helsinki showed the superconductivity in lithium. This is a very, very tough experiment, because lithium, you just take it out within a few seconds. Okay, it just becomes a powder. It's extremely reactive. So for that, they have to make a crystal, seal it, and then put the sealed one in thermal contact with the system. It's a mind-boggling experiment. No sane person will do, but Helsinki group are not sane people. So they did it and showed, and it became a big splash in Nature. So after 16 years for rhodium, 24 years, then we show that bismuth can superconduct. So this has an interesting history. So I told, I built the dilution fridge, microkelvin fridge with another student, Naren, who couldn't, reap the benefit. He set it up. By the time he set it up, his time is up. And luckily, I had another problem for him called the strongly correlated superconductor. He got his PRL and he got out of the system. And then Ohm came in. And Ohm spent nearly about 2 years to build this magnetometer, because, you know, magnetometer is the important instrument to pick up this signal, you know, bulk signal from superconductivity. If it is done by the magnetometer, people outside believe that it is a Meissner effect. Resistivity, nobody believes it so easily, because it takes only one filament to show you the resistivity, you know, in a matrix. Whereas expulsion of the magnetic field is a bulk effect. So unless the bulk is superconducting, you are not going to see that signal. So he built that. And as I said, you know, the Nature earlier rejected our paper, not even for a review. Now they would like to have invited me, and they said they will assure me a priority handling. And in this, I'm requesting Rajdeep to help me out because we have experimental result. It has to be backed by a solid theory. There's many of the theories which I'm going to tell you briefly are not going to work. So bismuth has been there for 100 years. Okay, all the important properties of solid state physics came from there, which got into a textbook, right from diamagnetism, Kapitsa, Shubligor-Diaz oscillations, and so on. Everything came from bismuth. And people thought that in the 70s, everything has been done in bismuth. It's done and dusted. It comes back with a vengeance. So you see that, you know, metal insulated transition, non-integrate metallic states, phase transitions in bismuth, all kinds of things in nature, science, and whatnot. Then our people, you know, our high energy people did and showed that no, bismuth is not a material, it's radioactive in a sense that it has an alpha activity. For the alpha activity, you know, it cannot come out. So, you know, it's that way it is safe. And then the, you know, half-life is a billion times more than the age of this universe. So it's going to there, you and me are not there. So, but bismuth is happily used in medicine, you know, which you take it for your stomach upset or something. So bismuth that way, it's a unique element, and it has an extremely small Fermi surface because its carrier concentration is small. It occupies just 10 ppm of the Brillouin zone, has a low carrier density, extremely large mean free path. It's of the order of micron at room temperature, and it goes to several millimeters at low temperatures. You know, it's so the electrons are ballistic out there. Yeah. Yeah, Fermi velocity for this is about 10 to the power of 7, something like that. Yeah, I think I will show you that graph later. So the important thing here is that its mean free this carrier density changes as a function of temperature. Unlike all its cousins like antimony, this one, and so on, this is something very unique. So far, there is not a single theory address this problem. It's been there for last 50 years. You don't have a single theory why the carrier density here. It's a semi-metal. Okay, so we will see that a little more later. So from the chemistry point of view, what is it? Huh? Hall. They have done, you know, 6-direction Hall effects and so on. So they have done beautiful experiment by the British group long back actually. So then, so let us try to understand from the chemistry that, you know, you have 6s2, 6p3 electrons in the outer electrons in the bismuth. Ideally, it should dimerize and become an insulator with a cubic structure. But here the Piles distortion strikes in. And it's so happened that energetically it is good to make this rhombohedral distorted lattice, which gains in energy and gives you a very funny band structure. If you look at the L point, the bottom of the conduction band is high, much lower than even the top of the valence band here. This is the crucial thing about bismuth. This has a very funny structure. And since the question first you ask is that with such a low carrier concentration, is bismuth a metal or a semi-metal? So important thing is this criteria, which is given by Mott, which is called Mott minimum metallic conductivity. That is, you have an effective Bohr radius carrier concentration should be less than 0.26. this is remarkably a nice rule, which is followed by oxides, intermetallic, chalcogenides, semiconductor, anything you take, it falls within this very, very nicely. I mean, that is one of the reasons why Mott got his Nobel Prize. So the point is that for bismuth, it's about 34. So we are in the safe limit. And not only that, here the bismuth is one electron is shared by 100,000 bismuth atom. That's why the carrier concentration is low. And so this is the band structure. So everything is known. There is a very nice Fermi surface measurements. All kinds of things have been done on bismuth. Everything is known from the electronic properties of bismuth. It has 3 electron pockets, tiny electron pockets, and 1 hole pocket. And those are the small area of the Fermi surface is what is responsible for the electronic properties of bismuth. And what I'm going to tell you is that to the one which is going to a superconductivity at 0.5 millikelvin. So Ohm did a crystal growth with Tamil Whale. I think they grown several crystals, I'm sure, that tens of runs and so on. But we got hold of a 69 pure, 99.9999 pure bismuth, on which we started growing this crystal. And so growing crystal is not it's a difficult task to grow at such high purity with strain-free system, but it's not impossible. So before we came into this picture, there was superconductivity in bismuth under pressure. Then there is an amorphous bismuth which shows superconductivity at fairly high temperature, 6K, nanowires. See, none of these things are not bismuth in its pristine form. Under pressure, the structure changes. You are not dealing with the pure bismuth, which is at the ambient pressure or temperature. So that's why I think most of the cases we can explain by BCS or extension of the BCS theory. And so the group at Helsinki tried to measure, which I mentioned to you, and they said, okay, 10 milli K, it's not going to superconduct, let's move on. So this led to a building of a ultra low temperature facility. So this is an interesting history in a sense that 1990, I came back fresh from Pabel's group, gave a colloquium here, Wiesing was sitting here. So everybody liked that colloquium. At that time, I was talking about nuclear magnetism of tRNA5 and related things. So then Wiesing asked me, this is all fine. What are you going to do here? So I said, build a nuclear refrigerator. So there was a dead silence from some audience. So I did propose, I think in 92. And that time we required a princely sum of something like 25-30 lakhs to do that. And that was huge at that time. So yeah, I had to wait 13 years to finally get the money. That time it has gone up to 1.2 crores or something. I must acknowledge here late Prof. MB group. So he is the one who fought for it. He says, if we can't do a challenging experiment, and if you can't encourage them, if you can't do it, at least encourage people who wanted to do it. So he fought and with Shobo, the money was granted to me in 2006. And then I started working for it. In 2008 or 9, the fridge came, and 2012, we were up and running with the microkelvin facility. And meanwhile, of course, Richardson, who was a Nobel laureate in physics, low temperature, he was visiting us, visiting Partho and people like that. And then he got to know that I'm going to build one. And he looked at the site and, good luck, you might need more. And walked away. So anyway, when I finally showed that thing, he is one of the guys also congratulated me that this is probably the microkelvin fridge in the harshest environment I have ever seen. So but anyway, so those are the things. So we are third in the list. Now I think this the whole thing, we are able to cool 5 kilograms of copper down to 40 microkelvin. And this fridge, I'm exceeding my time. Just give me 10 minutes to wrap up. So unfortunately, it has turned out to be history plus talk. So we are the third in the list in the facility which were created. but I think next month it is going to BRC. So they are going to maintain this because it requires a lot of helium and a lot of things. But they have also said that complete access to TIFR and all TIFR units will have a complete access to that machine. They will keep it running and so on. So that is the story of Preach. I think I've skipped these things. This is the magnetometer, which took nearly 1.5 years for OHM to perfect, where we measure the temperature in the same platform as the sample is kept. I'm just skip that. Just I want to show you that it takes 7 days to reach microkelvin. So if you have a power failure, you start again. So this is why people were kept away from doing ultra low temperatures, because you need a stable supply, and we were lucky. Not only stable supply, we also need a separate ground. You know, I like my laser friend, but I don't like his machine. Because you know, when they switch off and switch on, it gives so much, injects so much current into the ground. I can't have the same ground line as what he has. And so what we did was somehow we cajoled the electricity guys, and Singh was kind enough to us, and then we made a separate ground for this slab, and then painted that line with black so that, you know, it looked like a neutral, so nobody will touch it. Otherwise, you know, once you make a nice ground line, slowly people will make this. So then we will be wondering where our signal is going back. So then this is suggested by Singh, you make it neutral, nobody will touch that. So probably our ground line is still painted. Already all people know this and started connecting, I don't know. So I think everybody helped. I mean, I must say that, you know, things, so it takes about, because we had to calibrate the sensors at millikelvin. It works up to 10 millik with the standard calibration, but every time you do the run, that platinum NMR has to be calibrated with respect to sensors at high temperature. Okay, so this is how you discover the superconductivity. That is, you know, superconductor, when cools to below its critical field, it expels the magnetic flux. So you can measure that expulsion by having a magnetometer. So since you developed a magnetometer, you must make sure that it works. So we took Pobel's sample, not his sample, it's our sample. That's why it's a little less than 350 microkelvin. His is very pure and so on. And so at least we see that our things are matching with the system, the magnetometer works. Then we did the superconductivity of bismuth, where we showed that, you know, it does really superconduct with the 5 microtesla. So many things which are missed by our experts is that the Earth's magnetic field is 50 microtesla. If you do the experiment now with just without shielding the Earth's field, you will never see superconductivity in any temperature. Okay, so we need to shield it below nanoteslas. There is a way to do that, and we did that, and then that's how we got the superconductivity, and we see it's a type 1 superconductor and so on. What we have done in the last 2 years, which is, I think before I took over as director, that we did the anisotropy. That was really hard because OHM has left. There was only one scientific officer with me, and we were doing the experiment. And it took us 2 years to finish this part of the graph, which I told you, you know, this one. So we see an anisotropy, and this anisotropy is temptingly suggests that holes may be involved in the superconductivity. But we have to be careful because bismuth has a large spin-orbit coupling. That also gives rise to this anisotropy. So I have dumped this problem with Rajdeep. I hope we will get something out of it for the Nature Physics soon. So then the other thing is the resistivity. Bismuth has a, you know, it's supposed to have a t-square dependence of resistivity right down to lower temperatures. But, you know, it deviates something like around 400, 500 millikelvin. It's no longer t-square. Worse, when you go down to lower temperatures, it behaves like a t to the power of 5. So there is something changing at 500 milli-K in bismuth. The electronic structure or something is changing, which is we are unable to see it. I mean, ideally you can do a Fermi surface, but doing Fermi surface at this one is going to be very, very, very tough task. Yes. Yes, so it is not very clear, and it fits to a simple, you can crazily fit this to a, block donation theory. So, but don't believe that theory. It is just that I showed you. It is something else is happening. The T⁵ is coming not because of block donation. It's something else is happening. We need to look at the Hall measurements at such low temperatures. This is something I don't have energy and time, but there is definitely a change in the electronic structure, and that is how I think bismuth is superconducting at 0.5 millikelvin. The reasons are not very clear. Then there are models, okay, models and more models, which shows you can have a phonon or non-phonon. And there is one compound which is quite similar to bismuth, is strontium titanate. Strontium titanate is an insulator. So if you take one oxygen atom out of these 10,000 oxygen atoms in strontium titanate, it starts superconducting. Superconducting at fairly high temperature for me, it's about 55, 60 millikelvin. So there is no theory exists there also. There what happens is even worse. The lattice energy there is more than the Fermi energy. So there are models with Gorko and all, everybody is with the hand. The situation there is not understood yet. So these are the two things. That had a carrier concentration slightly more than bismuth. Actually, even in 10 to the power 5 into 10 to the power of 17 electrons also show superconductivity there. Very tiny Fermi surface, something similar to this. So there is bismuth and there is strontium titanate. Let me just quickly move on to some theories. Professor Jha, long back in 79, did predict that bismuth might superconduct at 1 millikelvin using certain models. And unfortunately, when I told him that it is this, and so look at my model. So I said, you have said it's acoustic phonons, and acoustic phonons are not, plasmons are not there in the system, and the energy range is not there. No, but we need to check it. So it's still, jury is open on this theory. Except, they predict the transition temperature should be less than 1 millikelvin. That is true. That is what is happening. So we probably we need to work on this more than this, because I would love more than this theory to succeed than any of the other theories which is coming up later. Okay. Srinivasan was a student. I don't know whether you know him, Chini. He was a close associate of Bajji. I don't know, Bajji, you all know. All these guys, you miss a lot of things actually. Because all these people are individual characters who, what we do typically is that after 1 o'clock, 2 o'clock, our lab work is gone. So 3 o'clock we assemble in Bajji's room, where he has a lobe chew, and that's how I know how to make tea. They have a nice kettle, and that kettle is covered with some soft cover and so on, and that's how it seems you should stew these tea leaves. If you say something to this, you will get the wrath of Bajji. He will say that you don't know anything. He will say so. So, but then we discuss all under the sun, who should be the next prime minister, whether somebody is getting record. Then we have a person called Mahadevan from School of Maths. He used to say that he's the one who says I know many things, because he was from physics background, he knows mathematics. So then we had other people who said, then somebody said, asked, do you know the difference between Fraunhofer and other diffraction? So Mahadevan started thinking, now I know that you don't know something. So we had very interesting people. Chini is one of them. He was a student of Jha. Okay, so there is another group which is Tiwari. They think that we are talking about a very degenerate gas, and if you put the carrier concentration and see an average electron distance is about 185 angstrom. So it's really large, fragile Kuiper pairs. maybe two-body interaction is enough. You don't have to bring in so many interactions because, this coal gas, coal atoms, they do this two-body interaction quite a lot. So they brought all that machinery of the coal atoms thing to explain the superconductivity here. They did say the superconductivity is fine. It is TC is fine, but their critical field is way too small. It's about 0.16. So they again, of course, they get around to saying that the gamma is not measured properly and so on. Gamma is only 5 microjoule per mole Kelvin. Okay, so you need to be very, very careful to measure such a low gamma in these things. Maybe that varies, but that is not really an argument because you need to change the gamma quite a large to match this theory. So this also tells you partial explanation. There are many other people in this fray, about another 6 models. Gorko, till his last breath, did work on the bismuth, and in fact, his last mail before the day he died was he was saying that let's look at this fresh and so on. Unfortunately, he's no longer there. And Bhaskaran, of course, has this his pet model of residual superconductivity from RVB. Lard, you all know MSc, he's talking about fluctuating exciton. Then Patrick Lee thinks that it could be due to some Coulomb correlations which can give rise to an attractive interaction aided by the holes and so on. So none of these guys are able to fit to these results which we have got recently. And that's why I have requested Rajdeep to just see where we can go and so on to understand this. So I think the next story is going to be invite me for another colloquium because when I'm retired. So because I'm going to tell you about this Ginsburg, Larkin, Khrushchev's theory and how we can look for superconductivity at ambient pressure in certain superionic conductors. See, what we have done is this theory tells us that there is no limit of the. Personally, I believe that unless you have a carrier consideration of the order of 10 to the power of 17, 18, that's the area where you're going to see high TC superconductivity. Don't ask me how, but I can only just say this is my thinking is. And so this is what I told you, Pratap, that boron up to 0.5 only gives you 10 Kelvin. But this one goes up to 55, this Q carbon, because it takes a lot of carbon into this, lot of boron into this. So now we are on to this ionic conductors. See, the ionic conductors are generally, when you cool down, they become insulated. So, but there are cases where peculiar structural transitions, they can become a metal. It becomes a semiconductor and then become a metal. So I feel that, this offers a lot of playground to look at possibly. We couldn't get superconductivity of this material. It shows large diamagnetism, and large diamagnetism is a, indication of there is a change in the Fermi surface. And so it is going from started with a superionic conductor, went to a semiconductor, becomes a metal, a dirty metal, because so dirty metal at low temperatures. And so you can see that resistivity is of the order of milliohms, about 500 microohms and so on. And their magneto resistance is changing, but it is a metal. You can see that beautiful gamma T beta T cube at low temperatures. So, and it has this spontaneous electricity coming because of the transition for another day. And the band structure clearly shows that it is going from a semiconductor to a metal with overlapping bands and so on. So I think I've taken 15 minutes more. I should not have done that. But let me tell you, it's a 42 years of journey. Just give me some consideration that I could 5. So according to them, they are coordinates of the place where we plunder. We go there, use this, get some new results, then you get more money from your organization because you have discovered something. So it's like plundering, pirates going into various coordinates and plundering things and so on. So I'm thinking that maybe we are also a pirate, which with the old boat, we have come back. It wasn't new when we started, but I think we need to rebuild again and
This board is
look
still
for
on the
this.
shore, see?
So I thought this appropriate and ends with it. I thank all of you. I think, it has been a wonderful journey for me. And, after 4 decades, everybody will say he has no regrets. I have a lot of regrets. I going to miss this place, and I'm going to miss all these guys. I mean, not only my department, but also, all of you. I think it has been a wonderful journey together. Thank you.
Thank you very much. A big round of applause. Okay, so yeah, the question.
Isotropy that you are talking about, is it temperature dependent?
No, it's not temperature.
So that's the thing which I was wondering, like, you really get some low dimensionality, some effective low dimensionality at lower
No, the sample is aligned at the d-axis and we keep measuring the critical field. So if the anisotropy doesn't change, it's temperature. So that ratio is about 3.22. It's strangely close to the effective mass of holes in the both directions. There is a relation which connects the critical field to the effective mass, but I can't do that bismuth so easily because it has a large spin orbit coupling. The anisotropy comes from there also. So distinguish between these two is a problem. I would have loved if the spin orbit coupling is less.
The structure is highly three-dimensional. Then in-orbit coupling also,
May not work. But anyway, yeah.
that is the thing.
That is the thing.
Yeah, okay.
That's why I'm hoping that it could be linked to effective mass. Then if we can pin that it is holes, then the theoreticians would also be more interested to do that. Because it's a difficult problem. It's a difficult. Hello. Yeah, sorry. Yeah, please.
So, Ramki, in bismuth, what happens in the case of quench condensed amorphous bismuth? Means it's the same element.
Yeah. So
The carrier density, is it so different that TC goes so high?
So the lambda goes up to 2.1. See, they have done the tunneling measurements on this, proximity tunneling or something. So there they have extracted the lambda from there. And it's about 2.1. And that's how it pushes the TC. The density of state is also changing rapidly. See, the bismuth that way is very, very sensitive. Even if you put few kilobars, it's going from the rhombohedral to a monoclinic quickly, then the band structure changes horribly. Even if you make it thin films, there is a dimensional change of the Fermi surface. So that's why you need to work. If you are to work with pristine bismuth, then only you can do that. Anything you touch, it is going to be a problem. Vivek?
Yes, so Ramki, bismuth has the very low charge carrier density, 1 in 100,000.
Yeah.
So that means your virtual phonons will be very low,
Yes.
through which your electrons are coupling.
Yeah. No, I am not saying it is phonon. It is not phonons.
Okay, so that's the different thing in bismuth.
See, the point is that since the Fermi energy and the lattice energy are comparable, the adiabatic Mitchell's theorem fails there. So the Eliasberg theory, everything will be out of the window.
Okay. One more follow-up.
Yeah, please.
So if one wants to design a new material, what property of the material one should think of?
The $1 billion question. So see, I am thinking of after spending nearly 40 years, I think that if you have large number of atoms like 10 to the power of 10. Earlier people thought that it should be 10 to the power of 21 electrons should be there, said TC and so on. I think that situation has changed. So I think we need to bring it down to a manageable thing there. And that's why I like this GLF theory. It says that what they have said that, you can't get superconductivity if it is carrier concentration is less than 10 to the power of 19 for a normal semiconductors. That is non-polar. If it is polar, then they say that, the carrier concentration can be even lower. So my feeling, I mean, it's just a gut feeling. I may be 100% wrong in this as well. But if you have moderate number of charge carriers into the system, then it is possible to tune. The ones which is under high pressure, there is some reason to believe that the carrier concentrations are not at 10 to the power of 21. It's about 20 or so. That's what the preliminary measurement shows. So I feel that I think you need to look at things like superanic solids and so on, which can become a metal at low temperature. There are thousands which become insulated, but there are few which can do this. So there is no hard rule here. I mean, like Bednarz and Muller, they were not working with superconductivity. They were in magnetism. And they suddenly saw some drop, and that's it, rest is history. So, in condensed matter, basically it is experimental driven physics. You see a new compound, new phenomena. If you look at how the high TC has come about, it's not the high transition temperature, amount of rich theories which has come. Beautiful theories which have come, which some of them later verified and which was feeding back to this research. And ARPES, everything about ARPES, came with a strong theory support. Otherwise we wouldn't have understood many of the surfaces. So new material drives new physics. And I think that's the way I say the chemistry guys, in my days, the chemistry guys are not interested in superconductivity. They the A15, it's all structure long back. What is this? It's all finished. So they are more interested in the structural form, but situation has completely changed in the last 1 decade or so. And our guys are bustling with so many things and so on. I think future is chemistry of materials.
Well, I just want to add that if the chemist said that experiments are driving the chemistry, it would be an uproar amongst the physics community. You don't understand anything. But anyway, so let's.
Can I ask a question?
Yes. Sure.
Yeah, this is Sunil Gupta. Okay, so Ramki, a fantastic journey. Just 42 years, 42 more years to go. And thanks for bringing the 80s and 70s alive for at least for me. Okay, mention of Chini and Bajji and Arun and so on. My question to you is, if you had to do this journey all over again, what are the things you will do differently? Would you choose a different approach, or would you what would you do differently?
I don't think I will do anything differently, I say. The point is that at any stage, I didn't feel that I have taken a wrong choice or wrong turn. Somehow I was a little lucky in getting the nice people around me. In fact, I am indebted to my technical and scientific staff. I think, in this institute, you are all blessed with fantastic support from scientific, technical, and other systems. I have traveled far. Okay? I never seen, a scientific support and the technical support, and this one which you get. I think in the institute, it is something unique. And I think, I should have cracked the ITC problem, and I didn't do that. With this kind of a support, if you have not done it, this mistake is mine. But I won't do anything different. I mean,
Okay.
Yeah.
Well, that's wonderful.
Thank you, Shovik.
Hi, Ramki. Wonderful talk. So I just have a quick question about, you said that in bismuth for thin films, the TC is much higher. So is there any understanding why is it happening?
Yeah, so as I told you, that the band structure itself is changing. It's no longer the L point is lower than the T point which I mentioned before.
I see.
There is a strong change. So there is a strong change in the band structure. So that is the reason why we can say that.
But are there efforts for looking at like single crystalline thin films of bismuth, and have there been any?
See, the point is that you have to go very, very low, that at the nanometer level to get this effect there. there is also a confrontation because it's strongly sensitive to substrates.
Right, right.
Okay. And bismuth on nickel surface.
So there is idea that there could be some charge transfer. And
yeah. So that is the problem at this one. That is what is holding up.
I see. Okay.
Unlike chromium, it's been shown superconductivity now on an NGO substrate. So the chromium lattice is expanding. So the magnetism is suppressed. So they were looking for quantum phase transition by dimensional driven transition in chromium. But the chromium, you have to be careful because it can get oxidized and you will end up with a different beast.
Alok Ray.
Alak.
Yeah, wonderful talk, Ramki. I just had a question from a part of your, initial part of your talk.
Yeah.
You mentioned that experimental probes of electron-phonon interactions is somehow better done in terms by Raman spectroscopy rather than through X-ray measurements. Can you elaborate on this?
No. See, I was referring to this high pressure research, superconductivity in high pressure research, not on the research which I am doing. There, I think there are easier measurements to do. See, at such mega per million, 2.5 million atmosphere, it's hard to do studies which are, either in bulk or this, and even X-ray is going to be difficult. The Raman signals are very nicely coming out of these compounds, this H2S S mixed or carbon mixed. So that's how the Raman signal can be easily tracked and even get both structural and other information from this. So only for this high pressure research on superconductivity, the Raman things are pretty useful. So
what is the difficulty with the X-ray measurements when you have these high pressure situations?
Yeah, so the point here is that because it is all done with the diamond anvil and so on and so forth, the resolution of the X-rays are getting limited out there. Okay. And of course, you can go to synchrotron and get these things. But still, I think when the Raman active modes are there in the system, that gives much clearer signal than X-ray could give. That is because of this peculiar thing. That is all. It's not always that is true.
Okay.
Okay. Thank you, Alok. Questions? Any other question? If not, let's actually carry forward all the good thoughts to our canteen and have some snacks. And let's have a warm round of applause again for Ramki. Fantastic. Okay. So I would request we wait for the speaker today and then start our snacks, okay? Oh. Narrating that you are breaking the trend. I'm just thinking